This video will cover section 9.6, Counting Principles. The objectives will be to solve simple counting problems, use a fundamental counting principle to solve counting problems. So that will be the very first method we will be using. Then the second method is to use permutations to solve counting problems. And also the fourth one will be to use combinations to solve counting problems. The combinations, the formula to find the number of combinations is the same as the formula that we saw in section 9.5, the binomial theorem. So let's start with the first example, and it says, example 1, selecting pairs of numbers at random. This section presents a brief introduction to some of the basic counting principles and their application to probability. So for example 1, we have, you place 8 pieces of paper, number 1 through 8, in a box. You draw one piece of paper at random from the box, record its number, and replace the paper in the box. So this type of problems where we see the word replace, that will be very important. You may also see with replacement or without replacement. So I'm going to continue reading. Then you draw a second piece of paper at random from the box and record its number. Finally, you add the two numbers. How many different ways can you obtain a sum of 12? So for us to solve this problem, we could consider the numbers that are from 1 to 8. And for the first number, and remember we replace the paper, so that becomes important because for our second number, we still have the numbers 1 through 8. And so you could see here for this option, we could draw a 6 the first try and a 6 on the second try. And if we add those numbers, we will get 12. So they will have a sum of 12. Another way to get a sum of 12 will be with 4 plus 8, or 5 plus 7, or 7 plus 5. And those two are considered to be different because the 5, for the first case, the 5 comes from the first number, and the second case, the 5 comes from the second number. Then finally, we have 8 for the first number, 4 for the second number, which is the reverse of this other option to get a 4 and then an 8. So those different ways to obtain a sum of 12, if we count them, you could see that they are 5 different ways. The counting problem in example 1 can be described by saying that the random selection occurs with replacement. We put the paper back in the box so the same number could be drawn twice. Example 1 describes simple counting problem in which you can list each possible way that an event can occur. When it is possible, this is always the best way to solve a counting problem. It's probably the easiest, and we're going to do some more examples in a minute. However, some of the events that occurred could be impossible to list them because it will be a pretty large list. So in those cases, we will have to rely on formulas and counting principles, and those are the objectives of the section. So the very first method that we will use is what is called the fundamental counting principle, and the formal definition is inside this box. So if we have two events, event E and event 2, or event sub 1, event sub 2, they're two different events. That's why we use the subscript to differentiate them. And for the first event, E sub 1 can occur in M sub 1 different ways. So this will be the number of ways or number of possibilities, and here E sub 1 is the name of the event. So after E sub 1 has occurred, which is the first event, the second event, which will be, is denoted with E sub 2, can occur in M sub 2 different ways. The number of ways that the two events can occur is the product of those two, M sub 1 times M sub 2. Now it's important to notice that M sub 1 and M sub 2, they may or may not be equal. One may be smaller than the other, or they may be equal, and that's okay. So using that fundamental counting principle in the product of those number of ways, that's how we can get the total of the number of ways that a list of events could occur. So for example, here we have 3 events, and we have event 1, 2, and 3. And so to calculate the number of ways that the 3 events can occur, you multiply the number of ways for each event. So example 3, we have how many different pairs of letters from the English alphabet are possible. And in this case, we have 2 events because we're gonna make a pair of letters, so 2 letters. So the first event is the choice of the first letter. So since we have 26 letters in the English alphabet, we have 26 options for our first event. So let's say that drawing a letter from the English alphabet was E sub 1, and then the number of events right there will be 26. So that's why we have this 26 here. Now for our second event, it will be the same to draw the letters, and that will be the second one, and it is also 26. Now here I don't really find the place where it says with replacement, but I am assuming that we're not talking about physically pulling papers out of a box like the other problem said. It just said randomly selecting a letter. So because both of them, both of the numbers, so this will be for event 2, E sub 2. So the number of ways that this could occur will be the total number of letters in the English alphabet. So if we multiply those two, then they are 676 different 2-letter pairs for this problem. So, okay, so I'm gonna give you guys another problem, and I am sure I'm gonna include some of those on your homework. So for example, to dial a number, you typically will use the country code. For us in the US is a 1, and then you have the area code. And for example, if you are familiar with making phone calls to Mexico, the country code for Mexico is 52. But then for their city code, they have less numbers. So let's just concentrate on the US right now. Then we have, for the area code, we have 3 digits. And these 3 digits cannot be, they cannot start with a 0, or they cannot start with a 1. So the reason they cannot start with 0 is because back in the day that was the operator. So, and the reason it cannot be a 1, or actually, yes, it could be a 1. I'm gonna have to check on the book. Okay, so I did check with the textbook, and we know, now I know that the area code could potentially start with a 0 or 1. However, so what that means is that for the area codes, for the numbers within the area code, we have 10 options for each digit. Then for phone numbers in the US, they are 7 digits. Oh, I don't have space. However, for the first 3, we cannot use 0 or 1. That is a must. And so for the first digit of a local phone number, you only have 8 possibilities. So those possibilities will be from 2 to 9. Now for the second and third numbers, we have 10 possibilities. So those will be the digits from 0 to 9. And then for the third number, we also have 10 possibilities, so the digits from 0 to 9. And the same is true for the last 4 digits of a phone number. So if we wanted to know, and let's just concentrate on, like if you were just calling locally, if we wanted to know in how many ways or how many different numbers could be in a city that has, or in a group of cities that have the same area code, it will be the product of 8 times 10 to the power 6. And that will give us 8, and then with 6 zeros after that. So that will be 8 million. So certain cities, like New York, for example, they have more than one area code for the city. And then, for example, a state like New Mexico, they have 2 area codes for the whole state. So that can also tell you a lot about the population. So, for example, on your homework, you might have questions about how many ways could you have, or how many different license plates could you have. So if you have a question like that, you will have to consider if the license plate can have numbers or letters or a combination of both. And for example, if there are any restrictions, such as you cannot start your license plate with the letter A or B. So then you just need to be careful when you do your homework and read all of those extra conditions. So our next objective is the permutations. One important application of the fundamental counting principle is in determining the number of ways, and we will call that n. Sorry, actually, this is different. The number of ways is one thing, and then n elements will be the other thing. So they're different numbers. Could be arranged. And for this one, for permutation, the order is extremely important. So can think about being in a race or being in the Olympics. It's not the same to win first, second, and third place. Just like it's not the same to get the gold, the silver, and the bronze medal. So in that case, the order matters, and we will be using permutations. So an ordering of n elements is called a permutation. So the word order and permutation, they go together. And this is very important when you do your homework and your exam. The definition of permutation, we have it listed here. So a permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. Another very common example of a permutation is, for example, running an election for student council. And let's say president, vice president, and secretary are the three things they're running for, or even more positions. So if you were just to vote and base the who gets pressed to be president based on the who gets the majority of the votes, and then secretary will be the one who gets the least amount of votes, then that will be also considered a permutation. Very common example is if you have the words the letters, sorry, A, B, C, D, let's say, and we ask, in how many ways could you arrange three letters? So out of four letters, you want to make groups of three. So for a permutation, having the combination A, B, C is not the same as having the combination BAC, and it's not the same as having the combination, let's say, BCA. And I believe there might be one more that I'm missing. Let's see, what if we put them in reverse? So it will be like CBA. So that is also, even though we have the same group of letters, all those ordering of the letters are considered different. And that is a permutation. So how many permutations of the letters A, B, C, D, E, and F are possible? So in this case, we could, and I don't really like the way this question is formulated, but let's just try to work with it. So for example, if we say it's not really implied that they will not be repeating, but think about it. If you are in a race, you cannot win first place and second place. If you win first place, then you are not going to be running for second place. And if you win second place, you're not going to be running for third place anymore. So in this case, we will assume that this is without replacement. So we have 6 letters, 1, 2, 3, 4, 5, 6. So we're gonna have 6 spots for our letters, and we're gonna write down that at the beginning for the first position there are 6 letters to choose from, which is all the letters listed here. Now, provided that, of course, one letter was already selected, then only the remaining 5 letters will be the number of options that you could have for the next spot. And then, in the same way, for the next spot, we will have 4 letters. Then we will have 3 letters, because we're eliminating 1, then 2 letters, and then at this point there's only 1 letter left, and so it will just be times 1. And if you remember section, I believe 9.1, we talked about factorials. So if we were to write to expand 6 factorial, you know very well that it will be the product of 1 times 2 times 3 times 4 times 5 times 6. And this is exactly the same thing as the product that we see here. Is just written in reverse order, but because multiplication of numbers is commutative, they have the exact same value. So for this case, we have 6 factorial, which will be equal to 720. And so this is the way that we could arrange the letters. in how many ways. Right here we have the same illustration, so same thing. Here we will have the letters from A to, I believe it was F, from A to F. And so let's assume that we get the letter F here. So then for the next spot, we will have the letters A through E. And let's assume that we get A. So now we already took 2 of the letters out of our 6 choices. So now we could get, let's say, from B to E. And let's assume we get E. So now out of the 6 choices, we already have chosen 3. So we have 3 letters left, and those will be B, C, and D. So for the next number, or I'm sorry, position, we have the options from B to D, and let's assume that we get B. So now for the next one, we are going to have from either C or D, and let's assume that we get C. And so the very last option, we have just one of them, will be D. So that is just one of the 720 different ways that you could order your letters. So for example, that was a question about license plates. And let's say that you have 26 letters. So let's assume that a license plate has 3 letters and then it has 4 numbers, for example, or digits from 0 to 9. So in this case, we will have 26 combinations. Oops, not 22. 26 combinations, 26 combinations, 26 combinations, if the first 3 were letters, and then the last 4 were digits from 0 to 9. So we will have 10 combinations, 10 possibilities, 10 possibilities, 10 possibilities, 10 possibilities. So then the number of license plates that we will get with this format will be the total product of 26 to the 3rd power times 10 to the 4th power. And I'm going to type that on my calculator. So 26 to the 3rd power and then times 10 to the 4th, so that would be times 10,000, 4 zeros. So that is what it will be, 175,760,000 license plates. Okay, so as you could see, the number of permutations, it is defined in general terms with the letter N, and that is the number of elements. And so just like factorial, it will be N times N minus 1 times whatever number is after in a descending order, the integer. And so it is the same definition as N factorial as we saw in section 9.1. So they do have that in common. In other words, there are N factorial different ways to that N elements could be ordered. So for example, if we had 3 elements, 3 factorial will be 3 times 2 times 1, and that will be equal to 6. So there will be 6 different ways for us to order those elements. It is useful on occasion to order a subset of a collection of elements rather than the entire collection. For example, you might want to order R elements out of a collection of N elements. And this is similar to what we did with combination. So NCR. We could also use this notation, N and then R here. For permutation, we will be using the label NPR. And the formula is a little similar, but still a little different. And that is because here with permutation, the order actually matters. Like running in a race, and it's not the same to get first, second, or third place. So such an ordering is called permutation of n elements taken r at a time. And so the definition is here, and it is also defined on the counting principle, but without repetition, of course. So it will be like n factorial. Another way to calculate it will be with n factorial on the numerator, and then denominator will be the difference of n minus r factorial. So example, we have 7 elements, and we want to take r at a time, but the order matters. And let's make r it could be from 0 to 7, so let's try a 5. So the formula for that, we have that n is equal to 7 and r is equal to 5. So this will be n factorial, so 7 factorial. And then on the bottom, we will have 7 minus 5 factorial. And at this point, we will find the difference before we calculate the factorial. So this will be 7 minus 5 is 2. So for 7 factorial, we could use 2 factorial, but then we would still have to write all the integers from 3 to 7 multiplying each other. But the reason we use 2 factorial is so that we can cancel it with this one. So then we just have to multiply the numbers that we see here. So 3 times 4 is 12. And I'm just going to use my calculator so I don't mess this up. So 12 times 5 times 6 times 7. And that will be equal to 2,520. Because the order matters. Now, if we go back to combination, which is going to come up pretty soon on this section, and we try to do the same problem, but in this case, it will be 7 and then combined with, I think we chose 2. So the formula here for n choose r is n factorial over n minus r factorial times r factorial. So in this case, if I substitute, this will be 7 factorial over 7 minus 2 factorial. And I think I made a mistake here. Oh, I don't want 2, I want 5. So we're going to make this a 5. And then times 5 factorial. So this will be 7 factorial over 2 factorial times 5 factorial still in the denominator. So in this case, we could use the biggest of 2 and 5 will be 5. So we will use 5 factorial here, then times 6, and then times 7. So on the bottom, we will have 2 factorial and then 5 factorial. So here, 5 factorial will cancel out with 5 factorial because it's equal to 1. So it will be 1 times 6 times 7, and that is 42. And then on the bottom, we have 2 factorial, which is 2 times 1. So 42 divided by 2 is 21. So you could see that when the order is not of importance, we get 21 different ways. But when the order matters, it makes sense that we get more ways. And you can see there's a big difference with combination and with permutation. And so all of that, I believe that's probably the toughest part of this section, to decide if you have to use combination or permutation. Remember that for permutations, the order is important. So to find the possible permutations of the letters A, B, C, and D, taken 3 at a time, you count the permutations of ABD and BAD as different because the order of the elements is different. And so I did explain this in a few slides back. So A here is in the first position, and the other combination or permutation is giving us A in the second position. So those two are considered different. Suppose, however, that you want to find the possible permutations of the letters A, B, and C. The total number of permutations of the 4 letters will be 4p4, and that will equal to 4 factorial. So if we use the formula, this will be, we're saying that 4 factorial divided by 4 minus 4 in parentheses and then factorial. So we have 4 factorial on top, and the bottom will be 0 factorial, and we know that by definition 0 factorial is equal to 1. So this is equal to 4 factorial. However, not all of these arrangements will be distinguishable because there are 2 A's in the list. To find the number of distinguishable permutations, you can use the following formula. And here what we have is n factorial, which is the number of objects, and one kind, actually that's the number of total objects. So this is the objects within the whole set. Then for each subscript, for each little number, n sub 1 is one kind of object. N sub 2 is the other one. And they are actually denoting the number of the objects of that same kind. And then for a third kind, we have this many, n sub 3, and so on. So the number of distinguishable permutations of n objects will be n factorial on top, the total, and then on the denominator we'll have the product of the factorials for the number of each different kind of objects. So for n sub 1 we have n factorial, n sub 1 factorial. For n sub 2, for the second kind, we have n sub 2 factorial. For the third one, we have n sub 3 factorial, and so on, until we get to, and here we're using the letter K to denote the last subscript, which will be the last kind of the number of objects that we want to work with. So K will be kind of like your limit. This could be, I don't know, it could be 4, it could be 3, it could be 100, it could be 5, but just a positive integer. And of course, K will have to be either less than or equal than n. It cannot be greater because we cannot have more than the total of objects in different kinds. Even if every object was of a different kind, you could not have more than n different kinds. When you, well, so now that we know that permutation is defined as something where an order matters, now we're going to move on to combinations. And we already described how the difference is that the order does not matter in combinations. So a very simple question could be, the House Senate is choosing numbers, not choosing numbers, choosing members of the Senate or senators to form a committee. So let's pretend the committee has 10, 10 members. So this will be something like, in how many ways can 52 senators be combined or chosen 10 at a time to form a committee, and just assume this is randomly happening, which we know is not the truth. But that would be a good example, because being just a member of a committee, you could be member one, member two, member three, and have the same importance. However, the president of that committee, or whoever's in charge, it does have more, um, not value, but it can make the decisions for more decisions for the committee. So, but let's assuming they all have the same role, then it will be a problem with combination and not permutation. Not like being president, vice president, and secretary. That would be permutation. Selecting a committee, combination, because the order does not matter. As a final topic, like we saw on the list of objectives, we will look at this method and the formula. And of course, we're familiar because from, what was that, 9.5, the binomial theorem. The formula is the exact same. I keep saying that. And it was the same formula that we used to find the binomial coefficients. So n factorial. On the bottom, we have n minus r factorial, and then times r factorial. For instance, when we talk about combinations, the combination ABC is the exact same as BAC. Even though their letters are ordered in different order, we're not talking about permutation. So in combinations, they are the same thing. They are equivalent because they contain the same three elements, the same three letters, and here the order is not important. So you will only count one of the two sets instead of saying that here we have two different. We just have one. So a common example of how a combination occurs is in a card game in which players are free to reorder their cards after they have been dealt. So, for example, in poker, you, depending what kind you play, you could be dealt 2 cards or 5 cards, but eventually you have 5 cards at the end. And let's pretend that you get a 2 of, let's say, clubs. And then you get a 3 of spades. And then let's pretend that you get an ace of hearts, and then you get an ace of diamonds, and then you get a, let's say, you get a 3 of hearts as well. So you could say that you have 2 pairs because you have a pair of aces, but also you could reorder your cards. Perhaps when you show your cards on the table, you might want to do that to make it more obvious that you do have 2 pairs. So it's not like people can say, oh, well, your spade is not next to your heart, so it's not 2 pairs. So that's a very good example of a combination. The order doesn't matter. You could always rearrange your cards. So for example 8, we have in how many different ways can 3 letters be chosen from the letters A, B, C, D, and E. So in this case, we have a total of 5 letters, N equals 5, and we want to take 3. We want to make groups of 3. So then R will be equal to 3. So in this case, it says in parentheses, the order is not important. So that's very important when you do your homework to read those instructions. So in this case, you could see that we have ABC, ABC, and we do not have anything like BAC or CBA or CAB or I can't really think of what else. CBA. Okay, so let's just use those 3 for example. We don't have those listed because they are considered to be within the same group because the order does not matter, and that is true for combinations. Permutation order matters, combination the order does not matter. So the combinations that we can have will be either with ABC or ABE or let's see, ABD. Or we could have ACE, ACD, and yes, or we could have BCD or BDE. But in this case, the total number will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's see if this will be true if we were to use this formula. So it will be 5 factorial over 5 minus 3 factorial and times 3 factorial. So 5 factorial over 2 factorial, 3 factorial. Instead of 5 factorial, I'm going to use 3 factorial because I'm going to cancel it with the one on the bottom. However, I still need times 4 times 5. And the bottom, we could see 3 factorial, and then we have 2 factorial, which is just equal to 2. So at this point, we can cancel the 3 factorials, and we will have 5 times 4, which is 20, and then divided by 2, so that is equal to 10. And those are the 10 different ways that you can combine 3 letters from a set of 5. The order doesn't matter, remember that. So here's the formula again. It's the exact same formula that we used last section in 9.5. And here we have the formula for permutation being used here, and it's just the difference between both is that they have that R factorial on the bottom, the combination. So for combination again, well, that one we have it written here, so I don't need to write it again. But for permutation, I'm going to write it here on the side. So it will be n factorial over n minus r factorial. So you could see that if you want to go from this one to this one, the only thing missing will be that r factorial that we see there. And so that's what they're showing here. So this is just a final summary. Combinations. So when you're doing your homework or solving any type of problem that involves counting principles, permutations, combinations, you need to ask yourself the following questions. Is the order important? If it is, then it's a permutation. Are the chosen elements a subset of a largest set in which order is not important? So if it's not important, then we're talking about a combination. And does the problem involve two or more separate events? Then fundamental counting principle, but then you will enter into this other two conditions. So this is the end of the video.